Welcome back to the ChemDoctor, and this video will be specifically directed at what are called heterogeneous equilibriums, and this video is in the playlist that deals with chemical equilibrium in general, and it comes on the heels of several videos that dealt specifically with doing equilibrium calculations. Now, what is a heterogeneous equilibrium? So if you look at this chemical equation, specifically at the components that are in it, you'll notice that unlike the reactions that we've been dealing with up to this video, that one of the components is a pure solid, whereas the other two compounds that are involved in the reaction are in the form of gases. So if I was to draw a picture of the reaction vessel that this thing is in, and we'll just say for the sake of argument that we're in a 1 liter flask, fixed flask. All right, so I'm going to seal this thing off, and it's 1 liter, the volume is, okay, and in the flask, this is what it's going to look like. This is graphite. It's a pure solid indicated by the S. And so I'm going to show that inside the flask by just drawing a little pile of it here on the bottom. And being a solid, remember that in terms of physical properties, this material is not going to expand to fill the volume of this container. So the densities, specifically the density of the graphite that's in this container is fixed. So density of carbon is fixed, and it does not depend on the volume of the container. And in fact, it only depends on literally the molar volume of the solid itself. And as long as this material is present in the reaction flask, its density is not going to ever change, no matter what the equilibrium positions are over the course of any kind of reaction here. So in other words, if we set up a chemical reaction, we let it come to equilibrium, all right, and at equilibrium there's going to be a certain amount of carbon dioxide in the reaction vessel, and there will be a certain amount of carbon monoxide in the reaction vessel. And the individual densities of each of these compounds is going to be dependent on the total volume of the container, and literally the number of moles of each of these compounds that exist at equilibrium. So the point being that at equilibrium, if we manipulate the equilibrium of this chemical reaction, the individual densities of the carbon dioxide and the carbon monoxide are going to change in response to whatever kind of pressure we exert on the equilibrium of this reaction. However, the carbon itself, which is in a solid form, as long as we have some of it present in the reaction vessel, its density is going to remain fixed no matter what the equilibrium position of this reaction is. So this means that when we write the equilibrium expression for a reaction that has a heterogeneous equilibrium, that expression has to be written differently than an expression we would write for a reaction like the one I'm showing here on the right side of my screen, where the components are all in the gas phase, or reactions that have components that are all in the aqueous phase, where concentration of the material can fluctuate for each species depending on what the equilibrium expression is. So if I was to write the Kc for the reaction here on the right, what we would write for this would be concentration of NH3 raised to the second power divided by concentration of the N2 raised to the first power times concentration of H2 cubed, where all the species appear in the equilibrium expression, because each of the concentrations of these species is going to fluctuate depending on the equilibrium position of this reaction. When we come back over here on the left, and we write the equilibrium expression for this chemical reaction, which is a heterogeneous equilibrium, where one of the species is either a solid or a liquid, the solid or the liquid is not included in the equilibrium expression, because its individual density or its individual concentration does not change over the range of equilibrium positions that are possible for this reaction. So we would write the equilibrium expression this way for this reaction. It would be written as concentration carbon monoxide raised to the second power over concentration of CO2 raised to the first power, noting the fact that the carbon is not included in the equilibrium expression. Okay, and this is going to be true for any component in a chemical equilibrium where that component is either present in the solid or liquid form. Now, let's look at another example, and the other examples that I want to look at here I've chosen because they're going to be relevant to the viewer in other systems that you study this year. The first one that I'm choosing to look at is what we call the autoionization of water, and I raised this issue before in the videos that I did on pH, where in liquid water you can have what we call the autoionization. So a certain amount of the liquid can ionize to form H3O plus, which is aqueous, and OH minus, which is aqueous. Now, again, the H2O in its liquid form, okay, its individual density is fixed. I'll just draw the arrow up here. So the individual density here of the liquid, so density of liquid, and I'll just abbreviate that, is fixed. And in fact, you can calculate the concentration of pure water a number of different ways, and I don't want to get off track here, so I'm just going to give it to you. It's actually 55.5 molar for pure water. And that concentration is going to remain fixed throughout this autoionization. I pointed out that if we use conductivity measurements, for example, to measure the amount of free H3O plus and OH minus in liquid water, what we find out is that the concentration of these two species is 1 times 10 to the minus 7th. So we would write the equilibrium expression for this reaction without the H2O present in the expression, because again, its concentration is fixed throughout any number of equilibrium positions that this reaction would take on in regard to the concentration of H3O plus or OH minus. And we're going to designate this equilibrium constant as a Kw, meaning that this is the equilibrium ionization constant for pure water. And its expression will be written this way, with concentration of H3O plus times the concentration of OH minus, and its value at 25 degrees centigrade is going to be 1 times 10 to the minus 14th. And just to remind you, going back to previous videos, therefore the concentration of H3O plus in pure water, which is equal to OH minus, is going to be 1 times 10 to the minus 7th molar. All right, now another example of an equilibrium that you will have exposure to probably at the same time or in the same chapter where you're dealing with chemical equilibrium in general, although it could come later depending on the professor or the teacher, is the situation where you're dealing with a precipitation reaction. So let's say that we're going to combine barium nitrate, and this is one of the precipitation reactions I dealt with in previous videos that focus on precipitation specifically, where we combine barium nitrate, for example, with sodium sulfate, Both of these reactants are aqueous, and we produce an ionic solid as one of the products, barium sulfate, and we are left with sodium nitrate, which is remains in solution. So if we were to look at what this appears in a beaker, all right, we would have this beaker full of a clear solution, and at the bottom, let's see if I can get this, if I can do a coloration here. At the bottom would be, this is supposed to be white, would be the white solid, which would be the barium sulfate. Now the barium sulfate, oh, and before I get to that quickly, what we have in solution above the barium sulfate is the sodium nitrate, which remains in solution and is not part of the equilibrium that I'm going to talk about next. So the barium sulfate is what we call a sparingly soluble salt. In other words, to the naked eye, this material looks like it forms an insoluble precipitate, but it is going to be in equilibrium with the solution that is sitting above it. And so some of the barium, albeit a very small amount of it, is going to be in equilibrium with the solid. Similarly, the sulfate ion or anion, like this. Now, again, the solid here is, its density remains constant essentially over the course of any variety of equilibrium positions between itself and ions that are in solution. And we can write an equilibrium expression for this. We're going to call the K now a new type. We're going to call this KSP for solubility product. This is an equilibrium constant for the solution of ions from a sparingly soluble salt. This is a salt that essentially does not dissolve in water, all right, and it will be equal to the barium ion times the sulfate ion. And again, the solid in this case does not appear in the equilibrium expression. Okay, now with that, I'm going to go ahead and close the video.